Assalamualaikum and very good day to everyone. So today we will continue the last topic in the potential electrostatic field, which is regarding on the potential gradient. Okay, which is regarding on the potential gradient and energy density in the electrostatic field. So these are the learning objectives that should be able to achieve by the end of this topic, where you will learn how to calculate the electric field intensity by using the potential value, and also the energy density calculation of charge structure. Okay, so far we have learned about the types of charges, where we have a point charge, line charge, surface charge, and volume charge. So all of this row is known as charge densities, and we have learned how from these charge densities how to calculate the electric field intensity by using the Coulomb's law, and also we have learned how to determine the electric flux density by using the Gauss law, which is closed integration d dot ds is equals to q enclosed. And also we have learned how from the charge density to measure the electric field intensity by using the d is equals to epsilon naught E, right? Okay, and also we have learned about the from the electric field intensity, how to measure or how to calculate the absolute potential. Okay, the absolute potential where your initial position is located at infinity. Okay, you can use negative integrations E dot dl, right? And also we have learned previously which from the charges how to measure the potential, right? Which by using this formula, integrations of dq is over 4 pi epsilon naught r, where this dq, okay, where this dq you can just replace with value of rho l dl for line charge, rho s ds for surface charge, rho v dv for volume charge. All right. So today we would like to learn about the potential gradient, where from the potential that we have obtained, how we want to determine back the electric field intensity. So this is what we're going to learn or we're going to look today. All right. So we have learned that from the absolute potential formula, okay, we know the potential we're going to be q over 4 pi epsilon naught r, where r is the positions of your source to the point of interest, right? Your source to the point of interest. And alternatively how or we can determine the electric field, okay, which is the E, electric field intensity, okay, at point A, okay, by using the gradient of potential at point A. Okay, so how this we're going to be relate, or how we're going to use this. Okay, so let's recap what we have learned before. We have learned that V can be calculated equals to integrations of E dot dl, right? And this dl is depending on what types of orthogonal coordinate systems that relates to our system. Okay, for example, let's use Cartesian. Okay, for example, the Cartesian, okay, your E will be it will be the component of Ex on x direction, right, plus Ey at y direction, plus Ez at z direction, right? And that is the E component, right? How about the dl? So for dl, for Cartesian, it will be Tx at x, right? plus dy at y plus dz at z direction. Okay, so if we substitute inside this equation, okay, both of it, we will get, okay, v is equals to negative integrations of ex dx, right, plus ey dy plus ez dz. Okay, all right, so now let's we separate the v into all of this component, into x, y and z components. So if we separate it, it will become, okay, and we make it into a smaller parts, yeah, okay, integrations, right? Let's make it as a smaller part. So it will be dvx, okay, potential in x component going to be dvx is equals to, okay, negative ex dx minus, sorry, not minus, yeah, let's erase that. Okay, let's erase this. Okay, alright, so that is in x component. Let's in y component, it will gonna be dvy is equals to negative ey dy, okay, and dv in z component, it will be negative ez dz. Okay, all right. So if we want to make our objective now, we want to get the electric field, right? So in that case, yeah, for all of the component, I don't have enough space down here, I'm gonna write up here, yeah. So in x component, your E in x component, it will become negative dvx over dx. In y component, E in y component, it will become negative dvy over dy, and in z component, it will become negative dvz over dz. Okay, and let's say we want to relate this v and e. Okay, this v and e can be related using the Garrod operator. Okay, this is the Garrod operator. We call it as Garrod operator, where Garrod operator, okay, it says to us that it is equals to d over dx on x component, okay, plus d over dy on y component or y direction, plus d over dz in z component. Okay, so Garrod operator for the Cartesian, it gives us this. So we want to relate this inside all of this equation. So we can rewrite then our E, okay, our E to be, we combine all of this, yeah, we combine all of this, it will become d over dx vx, okay, in x direction, of course, yeah, plus negative, it will become negative. So instead of positive, it will become negative, yeah, because there is a negative here. So negative dvy over dy in y direction minus d over vz over vz over dz in z direction. Okay, so let's say we want to relate, or we want to substitute with this Garrett operator. So we can simplify all of this to become your E then, to become negative, because we have negative here, negative Garrett V. Okay, negative Garrett V. Okay, negative Garrett V. So, okay, I think I make a mistake or typo error here. So, can you please remove one of the negative here, So, it will become electric field intensity is equals to negative Garrett V at that particular potential. So, this Garrett or this gradient operator here is depending on orthogonal coordinate system. So if it is for Cartesian, you're going to give as such. For cylindrical, it will become as such, where you need to change the variables, And for spherical, it will become as such. You don't have to be worried. All of this will be given or will be provided to you if it is necessary in your test or in your exam. Alright? Okay, now let's look at example 1. Okay, so example 1. Okay, so example 1, they give to us the value of V, okay, the potential. So x squared y z plus 3. So we can say that this is the variables involved inside here is x, y, and z. So of course, it is in a Cartesian, Cartesian. Okay, it is in a Cartesian. Okay, so there are two things that we need to determine. We need to determine the E field intensity at this particular point. So the related formula that we're going to use is the formula that has been introduced to you just now, which is E is electric field intensity is equals to negative Garrett or gradient, V, alright, where V has been given to us. Okay, so the Garrett for Cartesian is given as, let's put the negative in front, it will be d on Vx over dx plus, because we have put the negative in front, so dVy over dy. Okay, I forgot to write on the x direction, y direction, plus dVz in z direction. Okay, so let's proceed the calculation. So if you proceed the calculation, you will get, we will get the equal negative 2 xy. You have to differentiate, it will be z plus 3 in x direction. Okay, negative, positive, gonna be negative, Okay, negative Vy, it will be x squared z plus 3 and y direction. Negative Vz, it will become x squared y, okay, in z direction. Okay, so now to get the exact value for the E, what you need to do, you need to replace the value of x, y, and z inside the equation here. So you will get your E to be, you just have to replace inside here, negative 2, the value of x is 3, the value of y is 4, and z plus 3, so negative 6 plus 3 in x direction. Okay, and also so for others, in y direction and in z direction. Okay, so you will get your answer. So it will be volt per meter. Alright, So now let's look question number 2, which is the second question, where the second question they ask about the charge within the cube. Okay, so the structure we're going to be the cube. So the cube is x, we're going to be larger than 0, y, your z is not larger than 1. Okay, so if we can draw the cube, it will be, or it's going to look like. So this is your x, y, and z direction. So your cube will gonna be up until 1. So not larger than 1. So this is how your cube will gonna look like, right? Okay, so this is how your cube will gonna look like, right? So we need to find what? We need to find the charge. So charge will gonna be rho v or q, yeah? Q or rho v. But then they said within the cube, meaning that inside the cube as well. So it definitely refer to the rho v. Okay, so how to use this or how to solve this? So we know from our Maxwell equation, okay, from the first Maxwell equation, which is T is equals to rho v, okay, is equals to rho v, right? And how to determine this rho v to find for the whole total rho v, okay, the q, we need to do integrations of rho v dv, right? So we have we don't have the information of d, but we have the information of e that we have obtained just now. So from the e that you have obtained just now, we can get our d, right? So because d is equals to epsilon naught e, right? So we can just use the e that you have obtained just now, alright? The e that you have obtained, the equation of e, yeah, that you have obtained. So you will get your d, okay, is equals to dx plus d over dy plus d over dz and dz. Okay, so this is equals to rho v. So so let's refer to this equation. Okay, you need to differentiate this equation. So you will get the first one, you will get negative 2y, yeah, negative 2y z plus 3. And for the rest, it will become 0, right? Okay, plus 0 plus 0. Okay, so this is going to be the equations for rho v. Okay, so your rho v is equals to negative 2y z plus 3. Okay, and then to get the total value within all of this q, so q will gonna be integrations of rho v dv. So your rho v is negative 2y z plus 3, and your dv will gonna be dx dy dz for Cartesian, right? Dx dy and dz. So if you solve this, okay, let's bring the negative in front. So when you solve this, so for dx, the limits will become 0 until 1, plus with your dy, so it's going to be 2y dy, so the limits also 0 until 1, plus for dz also integration z plus 3 dz, and the limit also 0 until 1. Okay, so you solve this, you will get your answer, and it's gonna be in coulomb. Alright, okay, now let's look another example, which is example number 2, where this example we have discussed in our previous lecture, where in previous lecture we did discuss how to obtain the V. Okay, we discussed how to obtain the V, and now currently what we need to do, we need to do reverse version where we need to find the E. Okay, if you still remember in previous lecture, I did provide the E and you need to determine the V. So now it is in another way around. So we need to obtain the E field at any point on z-axis and prove that the answer is similar to be given term in example number 5, which is in our previous lecture note. Yeah. So we know in our previous lecture, we recap, fast recap. So it lies on XY plane. Yeah. And then we find the V or the potential at anywhere along the Z, and we give the coordinate as 0, 0, Z if I'm not mistaken. Okay, so now we need to determine the E. So therefore the E is equals to negative gradient V, yeah, negative gradient V. So the orthogonal coordinate system we used in previous lecture is cylindrical, so we're going to use the cylindrical as well. So the E for cylindrical we're going to be, E is equals to negative dvx over dx in x direction plus sorry, not x, k. It's no longer in Cartesian, right? It is in a cylindrical. So dvr, right? dvr in r direction, okay, plus 1 over r dv in phi direction, okay, plus dv on z direction, right? Okay, so our variable based on our previous lecture discussed, right? It will not involve the phi and r. Okay, it only involve in terms of z. So of course this will gonna be 0, right? So your E will then become negative dv over dz on z direction, and okay, we need to replace the value of v here with this and do the differentiation, and you will get your E then become negative rho L r naught over 2 epsilon naught r naught squared plus z squared half, and if we proceed the calculation, okay, right, so this is the value of v, right? So we not differentiate it yet. I should write the d over to avoid confusing, right? Negative d dot dz, d over dz. So if we solve this, we will get our E to be rho L r naught over 2 epsilon naught z over r naught squared plus z squared 3 over 2 volt per meter. Alright, so please prove this. Okay, make sure that you are able to obtain the E field same as what we have discussed in our previous lecture. Okay. Now let's look into another example for this potential gradient. Okay, so this is also based on our previous lecture that we have discussed before, and example number 6. Okay, so in this case or in this lecture, you need to obtain the E field in terms at the following location where the radius based on the previous obtained potential terms, where your r is larger than r naught, and R is lesser than R naught and R is larger than R naught, and you have to verify your results using the common law. And if we can still if I can sketch back the one that we have solved previously. Okay, the radius is given as R naught and there are two fields involved, right? Okay, there are two fields involved, right? And if I'm not mistaken, the rho s, okay, is given as rho s, right? And there are two field there are two values of E. You have E inside the structure, and outside the structure is different, okay, because it is a surface charge. So of course inside here they're going to be 0, and so your E field now, inside and outside is different. Okay, so to find or to determine the E field, okay, you can use the V that we have obtained in our previous lecture. Okay, please refer that. So E is equals to negative Garrod V, and in this you need to use the spherical condition. Okay, spherical orthogonal coordinate system. Okay, so you need to determine when your R is lesser than R naught, okay, and when your R is larger than R naught. So I leave this to you because this is what repetitions from what we have done before. Okay, just a backward calculation method. All right. Okay, let's go into the last topic inside this chapter, okay, which is regarding on the potential, which is you need to know about the energy density in electrostatic field. Okay, so we want to know what is the amount of energy consumed in the system. Okay, for example, you have a system, and inside that particular system you have a multiple of charges, and we want to know the amount of energy that is consumed in this system, okay, that contains multiples of charges. All right, so what is energy? So energy is potential energy, and it present in such systems of charges. Okay, so of course it will relate with the work done by an external source in positioning or locating the charges. Okay. Okay, for example, now we want to calculate the work done by the external source. Okay, by the external source in order to position the charge. Okay, so there are several steps. Okay, let's do this step by step. So the first step, let's assume that we have an empty system. We have a system, and that particular system is empty, meaning that there is no charge exists inside that particular system. And now, when there is no charge exists, okay, this is to make you clear. When there is no charge exists, meaning that the E field also will be exist or not. It is not exist. Sorry, it is equals to 0. Okay. It is equals to 0, meaning that since that there is no source of charge, so there is no E field exists inside this system as well. So there is the E field is equals to 0. Okay, now we want to bring one point. Okay, we want to bring a point charge. Okay, we bring one point charge which is Q1. Okay, from somewhere around, somewhere outside of the system, and we want to bring it inside the system. Okay, since that we just bring it from somewhere else, and that particular system doesn't have any energy, so it doesn't require any work. So inside this, okay, when we bring one point charge into this system, since that the value of electric field is equals to 0, so therefore the work in order to bring this charge to this system also will become 0, because there's no work inside the system to resist or to avoid this charge from coming. Okay, so now inside the system we already have one charge, and what we want to do now, we want to bring another point charge. So we want to bring another point charge, which is now Q2, from the infinity as well into the system. Okay, now, when there is a charge already exists inside the system, what will happen? Of course, the electric field will exist. Okay, the electric field will already exist inside the system because it's already have a charge. And once we want to bring another charge to this particular system, what will happen? Of course, there will be there will gonna be a glitch, yeah, meaning that this particular charge will try to resist this point charge from entering. So since that this charge still want to enter to the system, it requires some work to be done. So the work will gonna be work at the beginning is equals to 0, of course, but when we want to bring this particular charge to the system that now already exists another charge previously, so it requires a work, and that particular work will then, the work is equals to Q E dot dl, if you still remember, right? Q E dot dl, and this E dot dl is what? Is V. So Q with the V, the potential. So the potential is where? Potential at Q2 due to the charge of Q1. Okay, so that's why the potential is written as 2,1, which is potential at Q2 due to the charge of Q1. Alright. So let's say we want to bring another charge. Okay, we want to bring other charge as well, which is now Q3 into that particular system. So at the beginning it is 0. Okay, so now work 2, yes, this work 2 now is already added, and now it requires more work since that there are 2 charge already exist inside the system, and we want to bring other to that particular system. Of course, requires more work. So now work required in order to bring Q3 charge into the system. Okay, it will involve the Q3 potential at Q3 due to charge 1, and also potential at Q3 due to charge number 2. Okay, alright, so that's why the equation becomes V31 and V32. So it represents the potential at charge number 3 due to charge number 1, potential at charge number 3 due to charge number 2. Okay, so now we can say that, okay, so now you notice that the Q2 V21 also can be written as such, and Q1 Q2 also, so it's same, yeah, Q2 V21 is same with Q1 V12. Okay, you just change the position of here. Okay, so what's are the difference here between these two? The first one, it is charge. You look at the respective charge. We are calculating the work at charge number 2. Sorry, okay, I erase that. Change color. We are calculating actually the work that is in order to bring charge number 2. Okay, the work in order to bring charge number 2, which respect with the potential at charge number 2 due to charge number 1. And for this one, it means, or it represents the work in order to bring charge number 1 in respect to the potential that is charge number 1 due to charge number 2. Okay, so it is actually the same. You don't have to confuse. It is actually the same. Okay, you just change the what is in front, what is what is posited at the in front here, and what is posited at the numerator here. Okay, so by interchange the subscript 1, the following energy can be obtained by Q1 V12, Q1 V13, and Q2 V23. Okay, so we can rewrite it as such, and from here the total energy, okay, the average energy. Okay, so the average energy, of course, we need to divide with 2, okay, because we want to know the average energy. So all of this summation just now you divide with 2. So therefore, the total energy in order to bring all of the charges to that particular system, it will become W, which is mean the work total, work done or the energy required, okay, equals to 1.5, because we want to have the average, right? Okay, the summations of how many charges to that particular potential, right? So in terms of other charges, we have others continuous charges. You have to replace the value of Q with rho L dl, rho S ds, or rho V dV. Okay, remember V is the potential at the charge distribution. Okay, there is another alternative way to calculate the energy density that has been introduced to us, okay, which is the energy density, which is the W, yeah. So just now we know W is equals to half, okay, half, please bear with my handwriting here, okay, half integrations of V dq, right? Okay, so now there's another alternative way, another formula that we can also measure the energy density or the work, yeah, which is equals to half, okay, integrations, but instead of V dq, we are using D dot E dV, okay, D dot E dV. So here I will not show to you actually how from this equation it can be represented into this formula. You can search by yourself in your reference book. There is in a reference book, they explain how from VDQ you can also calculate your energy density to become D dot E dV. Alright, so from here actually you can see the elements of D and E is almost the same element, yeah. Once you know your E, you can also know your D, right? Because D is equals to epsilon naught E, right? Epsilon naught E. So once you only need to know your E only, yeah. Okay, and from here, yeah, both of this, yeah, dot products of both of this, it will give to you a scalar form, and so therefore your work also will gonna be in a scalar form. All right, so it represents well, yeah. This one also is the previous equation also is in a scalar form, and this equation also is in a scalar form. So you can use either one, which one that you want to use to solve the questions, okay, as long as you have all the information. Let's say you have your V, you know your Q, so you can proceed with this equation. But let's say you have calculated your E earlier, okay, so in order to know the energy density, you can use this equation, right? So the equation state that energy in the system of charges can be obtained if the electric field distribution, which is incurred by the charge itself, is known. All right. So now let's look into example number 4, which is regarding on the energy density. Okay, so a spherical charge distribution of radius RA. So we know it is a spherical, so we use a spherical coordinate system, and has a radius of RA, and it has a uniform charge densities, which is rho V, is centered at the origin. Okay, so if we can illustrate, we have a radius of sphere, okay, which is given as RA, and inside here the charge is given as rho V. So if the total charge is Q, alright, so the total charge is given as Q, find the energy needed, okay, find the energy needed in order to build up the charge system. Okay, so we can use two kind of formula just now. So let's say we don't have any information of potential, right? But we can calculate the E, because E we can use the Gauss law here. D dot ds is equals to Q enclosed, right? So I think the most preferable equation that we can use is the this equation here. Oh, don't forget to write the half in front. Half integrations of epsilon naught E squared dV. Okay, so now let's use this one. So first of all, we need to calculate, in order to use this equation, we need to calculate the E field. Okay, we need to calculate the E field, but which area of E field? So in order to build the system, of course, we need to calculate in all cases, meaning that when your R, E field for your R is lesser than RA, which is inside the structure, and also when your R is larger than RA, which is outside the structure. Okay, and then we need to use what formula to calculate the E field? We can use the Gauss law, because Gauss law is easier for a spherical charge distribution, which is, and also a uniform, right? So we can use the spherical. So now let's get the d.ds equals to Q enclosed, right? So now let's use the first condition when your R is lesser than RA, meaning that your Gaussian surface is located inside the structure. Okay, so for your left hand side, okay, it's gonna be your D in your, and your DS is gonna be your D, of course, in R direction, right? So your DS is gonna be 4 pi R squared. And your Q enclosed is integrations of rho v dv, right? So integrations of rho v dv will gonna be inside the structure, it will be rho v 4/3 pi r cubic. Okay, so if we solve this left hand side and right hand side, so we can cancel this r, and then we can cancel this 4 pi. Okay, so it will left behind only your D is equals to your D is equals to, in region number 1, let's give the name of the region. Yeah, this is region number 1. In region number 1, your D is equals to rho v over 3r, right? In R direction, because it is dr just now. Yeah, in R direction. And your E, once you know your D, you can determine your E, right? So your E will then become rho v over 3 epsilon naught r in R direction. Okay, so how about for R larger than RA? When your R is larger than RA, okay, so your left hand side is still the same here. dr will gonna be 4 pi r squared, still the same, but now your Gaussian is located outside here at this outside area. So let's say this is region number 2, so it will be your Q enclosed now will become rho v dv, right? So it will become rho v 4/3 pi ra, alamak sekejap ya, pi ra cubic. Okay, because the radius now is ra, yeah, ra cubic. And what else? So if we calculate our D, you will get how much? You will get rho v RA cubic over 3R squared, right? So this is your D and your E. So this is for region 1, yeah. E for region number 2. You will get equals to, you just have to add epsilon naught, yeah. RA cubic over 3R squared epsilon naught. Okay, so now we have determined all the D and the E. So we want to determine the W, the work or the energy density. So the work total is equals to work at region number 1 in order to build the structure, right? Or to build the system. Work at region number 1 plus work at region number 2. So what you have to do, calculate one by one. Work for region number 1 is equals to what? Integrations of, okay, half. Don't forget to write the half. I always forget to write the half, yeah. Half integrations of epsilon naught rho v r over 3 epsilon naught squared, and the dv is r squared sine theta dr d theta and dv. Okay, so proceed with your calculation. Okay, you will get some value that is only for work 1, and then same goes to work at region number 2. Okay, I left it to you to solve. Okay, and then once you got all of this, you sum together and you will get the total work done in order to build the system. It's supposed to be in joule. Okay, so now let's look at examples. The last example in your slide, example number 5. A simple coaxial cable is made up of a central cylindrical conductor of 5 mm diameter with an outer conducting sheath, also cylindrical, coaxial with the central conductor. The internal diameter of the outer sheath is 20 mm. The space between the two cylinders is filled with air, and the maximum voltage that can be applied between the conductors is 500 volts. So we need to determine the energy per unit length in the given structure. Okay, so without any illustration given, so first we have to extract all the information inside this questions, and also then we need to illustrate. Okay, so first of all, it is a coaxial cable. So coaxial cable here. So and then what else? So coaxial cable, it is a cylindrical, so the variables that we can use is cylindrical, yeah. So it's gonna be R, V, and Z. Okay, so the conductor of 5 mm diameter, so it will be 2.5 mm in radius, right? In radius, with an outer conducting sheath. So it has an outer conducting sheath, which is also a cylindrical coaxial with a central conductor. So it has an internal diameter with the outer sheet is 20 mm. So it's gonna be 10 mm in radius, yeah. R. So the space between the two cylinders is filled with air, so meaning that it is epsilon naught. And when we apply the voltage between the two conductors is given as 500 volts. So we need to determine the energy per unit length, meaning that W over L. in the given structure. So if we can draw the structure, it kind of looks like we have a coaxial. Okay, first the inside here it's given as 2.5 millimeter. Okay, so inside here is 2.5 millimeter, 2.5, yeah, and remember it is in a millimeter. Okay, 2.5 millimeter. I think it's too small, make it a bit larger a bit. So we have 2.5 millimeter, 2.5 millimeter. Okay, and then in radius, and then it has another conductor. Okay, it has another conductor. So this is conductor, inside here is conductor, and this is a conductor. Outer conducting sheet, where the inner, so it is also a coaxial, right? Coaxial with the central conductor. Okay, so the outer conducting sheet also is a coaxial. So if we can draw, so this outer, okay, outer sheet, yeah, this is conductor, this is conductor. Okay, but then the inner, okay, the inner diameter ataupun the internal diameter is given as 10 millimeter. Okay, so outside here is the they didn't mention, yeah, how thick is this. Okay, so that is only the information that we have. Okay, another information, the voltage applied. So the voltage applied from both of this, which is from this conductor to this conductor, is given as 500 volt. Okay, alright, so that is only the information that we can extract from the questions. So between these two conductor, okay, some might assume, how about inside here, what are the types of charge that is has inside here, right? What type of charge that is exists inside here? Okay, you will learn this in the next following chapter when we goes into boundary, when inside a conductor, okay, inside the conductor there is no charge exists. Okay, the charge for a conductor material, the charge is only exists at the surface only. Charge only exists at the surface for a conductor. Inside here it is 0. So inside here it is 0. So let's assume the charge that is the charge, since it is only exists on the surface, so let's assume that this is going to be the positive charge. Okay, so therefore for the next conductor it will become negative rho s. Okay, so inside here and inside here there will be no charge. Why? I will explain this on the next chapter. Okay, on the next chapter when we go into boundaries. Okay, electric fields with boundaries conditions. Yeah, so now we know the equation that we will use or we will apply is W is equals to half integrations of d dot E dV. Okay, alright, so now let's find the E in all region. Okay, so E between, so since that there is no charge exists inside here, so of course there's no E exists inside that right? So E will then only exist when E in region 1, where your R is at when your R is between 2.5 millimeter to 10 millimeter. Okay, millimeter, we need to write this because this is not in SI unit, right? Okay, so we know the E it will become, based from the what we have calculated, it will become rho s 2.5 millimeter over epsilon naught r in r direction. Okay, so you can try to obtain this E. Okay, I will not show to you the calculation here, okay, because it got lengthy. All right, and then E lesser than E, when it is, your R is lesser than 2.5, it is equals to 0, right? Is equals to 0. And when your E for R larger than 10 millimeter, also it will become 0, because there's no charge exists at this part. Okay, there's no charge exists at that part. Okay, so we only need to consider at this region only. Okay, we need to consider only at this particular region only, right? So your work will then be half integrations of epsilon naught rho s squared, and then 2.5 milli, 2.5, I wrote it as milli here, squared over epsilon naught squared, and r squared, right? Then r dr d phi and dz. Okay, so we proceed with the calculation. So half, okay, and then we can simplify some of the equation. We can bring the constant in front. Let's bring all the constant in front. So it's gonna be rho s squared over epsilon naught 2.5 milli squared. I bring it in front and left behind all the integrations of r. Okay, it will become 1 over r dr, integrations of d phi and integrations of dz. Okay, so now let's decide the limit. So the limit from for r, it's gonna be only at this region, right? So it will be 2.5 milli. Don't forget about the milli, 2.5 milli until 10 milli. For phi, 0 until 2 pi. For z, it will become 0 until L, will be the height of the cylinder. We don't know, we just give it as height of the cylinder. So your W will then be, your work here will then be, your work will then become, okay, it will become rho s squared 2.5 milli squared, 2.5 milli squared over 2 epsilon naught 2 pi L and ln 4, yeah, ln 4. And if we simplify this, you will get W per L, because we need energy per unit length, so W per L, so it will become rho s squared 2.5 milli, don't forget to write the milli, okay, 2.5 milli squared over epsilon naught ln 4 in joule per meter. Okay, so you will get this answer. Please simplify this, right? So let's do the fast recap what we have learned so far. We have learned the concept of work and energy in the electrostatic field, where we have learned that W is equals to negative Q integrations of E dot dl, right? Okay, and your DL is not depending on the path taken, right? And we also have learned about the second Maxwell equation, which is the closed integrations of E dot dl is equals to 0, right? And we also have learned about the concept of potential difference and absolute potential. Okay, and absolute potential, where from here we have learned about W over Q. Okay, W over Q is equals to VAB. Okay, is equals to negative where it start at B and at A, E dot dl, right? E dot dl, so this is equals to VA minus VB, right? So this is the potential difference, and also the absolute potential, where the origin or the initial point is become infinity, okay, when your B is approaching infinity. And then we also have learned about the potential gradient concept, right? Potential gradient concept, where E is equals to negative Garrod or gradient of V, okay. And we also have learned about the storage energy calculation, where there are two ways to calculate that, okay, in a system. Okay, storage energy inside a system, where there are two equations that you can use. Half, first one, D dot E, this is the famous one, yeah, D dot E dV, and another one is half V dq. So you can use either one, alright? So for our next lecture, we will go into the concept of electric current and also the conductors and conductivity. It will gonna be helpful if you can do your preliminary reading or study about these topics. Thank you so much.